The overall goal of the following experiment is to synthesize single-walled carbon nanotubes and graphene in arc simultaneously. This is achieved by first preparing two arc electrodes, anode and cathode. The anode is prepared and is fabricated with a specific ratio of carbon, nickel, and yttrium of 94.8 to 4.2 to 1, and the cathode is a pure carbon rod. Then, numerical simulations presenting the distribution of the magnetic field and species particles are used to provide the detailed information about the location of synthesis. Then, the magnet and the molybdenum sheet, which functions as a substrate, are installed according to the simulation results, and the arc discharge between the electrodes is initiated. A plasma jet is formed, and it deposits single-walled carbon nanotubes and graphene on the surface of the molybdenum sheet. In the end, this procedure shows high-purity single-walled carbon nanotubes and graphene based on transmission electron and scanning electron microscopy, electron diffraction patterns, and Raman spectrums.
Visual demonstration of this process is crucial because this is, extremely complex, process that has, many steps, and in particular in the case when non-uniform magnetic field is used. As far as plasma-based process of synthesis is concerned, it has many advantages in comparison with chemical-based process. In particular, it doesn't require chemical exhaust, so it's green in the nature. In addition, it has tremendous potential for large-scale development.
The main advantage of this technique over existing method, such as chemical vapor deposition, is that it can synthesize a single nanotube and a few layer thick graphene in one simple step in arc discharge.
So this experiment basically demonstrates the methodology of how the control of arc discharge using external magnetic fields can be used in order to synthesize different types of nanostructures like nanotubes or graphene.
The design of this technique is based on Lorentz force in magnetically enhanced arcs. Also, the numerical simulation of distribution of magnetic field and species is crucial to understand the growth of nanoparticles.
To prepare anodes, combine nickel powder and yttrium powder at a molar ratio of 4.2 to 1 as the catalyst powder. Thoroughly mix the catalyst powder with graphite powder to obtain a ratio of 94.8 to 4.2 to 1 of carbon to nickel to yttrium, which is the optimum ratio to synthesize single-walled carbon nanotubes. Firmly fill the mixed powder into a hollow graphite rod. Install a cathode rod and the stuffed anode rod inside the cylindrical chamber. Adjust the gap distance between the cathode and anode to about 3 millimeters. To set up the substrate, place a cuboid permanent magnet inside the chamber about 25 millimeters away from the interelectrode axis. In this configuration, the interelectrode gap is set at a distance of about 75 millimeters from the bottom of the permanent magnet. Cut a 0.3 mm thickness molybdenum sheet into a 25 mm by 100 mm rectangle. Using an ultrasonic dismembrator with acetone and ethanol, remove the surface contamination for 30 minutes with a 50% sonicating amplitude, 150 watt output power, and 40 kHz frequency. Attach the molybdenum sheet to one side of the permanent magnet and turn this side towards the electrodes. Using a Gauss meter, measure the magnetic field in the interelectrode gap. Keep the average magnetic field between the electrodes at about 0.06 Tesla. To ignite the arc plasma, pump down the cylindrical chamber to a pressure of less than 0.1 torr of vacuum and then fill it with helium to 500 torr. Connect the arc electrodes to a DC welding power supply and set the power supply to an arc current of about 75 amps. Record the real-time values of arc current, arc voltage, and chamber pressure for post-experimental analysis. Start the video of arcing from the right and front viewports simultaneously with 2 digital cameras. Run the arc for 15 seconds. Cool down the chamber by natural convection for at least 20 minutes. When the synthesis is complete, use tweezers to tear off the deposition flake from the surface of the molybdenum sheet where the arc plasma jet was directed. Collect another sample from the black collar of the cathode. Observe the morphology of both sides of the deposition flake under a scanning electron microscope using an acceleration voltage of 30 kilovolts. To prepare samples for transmission electron microscopy, sonicate a methanol-dispersed single-walled carbon nanotube solution for 60 minutes using an ultrasonic dismembrator with 50% sonicating amplitude, then drop-cast the suspension. Observe the morphology of the film using a transmission electron microscope with a voltage of 100 kilovolts after the volatilization of methanol solution. For the position of interest in the sample, the electron diffraction pattern can be obtained with a CCD camera length of 50 centimeters. Observe TEM images of the synthesized structures. Observe the electron diffraction pattern of the sample. Shown here are video snapshots obtained simultaneously from the right and front viewports of the chamber for an electrode gap height of 75 millimeters. These images illustrate significant perturbation of the arc plasma column in the presence of an external magnetic field. These images display the typical morphology of single-walled carbon nanotubes and catalyst particles collected on the collar of the cathode without the magnetic field and with the magnetic field of B equals 0.06 Tesla under TEM, respectively. Nanotubes collected without a magnetic field form larger diameter bundles and larger individual diameters, which is consistent with the Raman spectrum analysis. The magnetic field also resulted in a more pure collection of nanotubes than without the magnetic field. Here is a Raman spectrum of samples in a range of 100 to 3100 per centimeter obtained with a magnetic field. The inset is for samples without a magnetic field around radial breathing mode frequencies. The intensity of the 2D peak over the intensity of the G peak is utilized to estimate the thickness of graphene layers. This spectrum produces an intensity value of around 1, which represents that the number of graphene layers is around 2. This animation shows the nanostructure growth region and number density of carbon, nickel, and yttrium for an arc current of 60 amps. Note that the densities of carbon, nickel, and yttrium shown on right, left, and vertical planes coexist in the same region.
After development, this technique will pave the way for researchers to work on magnetically controlled synthesis of both single-wall nanotubes and few-layer graphene, in which both single-wall nanotubes properties such as length and diameter can be controlled, and when it comes to graphene, the number of layers can be controlled. The main advantage of this technique with respect to chemical-based synthesis is that it doesn't require chemical exhaust and therefore it's green in its nature.
Once mastered, this technique can be done in 30 minutes if it is performed properly.
It's important to note that direction of plasma jet towards the substrate is very important for entire process of synthesis. First, plasma jet is delivering a carbon species to the substrate, which are required to synthesize a product. And the second, plasma jet delivers a heat flux to the substrate, which is creating favorable temperature conditions for synthesis of graphene.
Following this procedure, other methods like moving the substrate can be performed to answer additional questions like controllability of flake thickness.